Okay, so I am getting a few things together right here. Sorry, I'm off to a minute or two late start. Um, Hopefully everyone had a great weekend. All right, I'll give it a moment here for everyone to join us. I think we've got our usual crew. Um, let's see. Yeah. There we go. Okay. All right. So, let's get started. A few things to begin with. For one, all right. I'm gonna pull up the WIO courses page here. All right. So if we go to our class WIO courses page, um, one thing to notice is that in the files section or in the assignment section, you can find the key for homework 2. It's right in there. If you didn't notice, the key for homework 1 is there. It's also there as well. It's been there for a little bit. So we have that guy, and it goes through everything here. Fully worked out solutions, explaining everything. I think a number of people may have had trouble with a couple of the questions, so I wanted to really briefly touch on them. In particular, I think that number 3 and number 4 messed up some folks. So I just wanted to really quickly clarify that this was not intended to be like some brutally difficult exercise. I think I took this problem from out of the textbook, and I think its wording just might have been sufficiently vague that people made it more difficult than it actually was. In particular, this was not trying to get some very fancy thing out of there. Really, all we were trying to say was that a line parallel to the real axis, that is something with a constant imaginary part, a set of points with constant imaginary part, gets mapped to a parabola by the squaring map, the map that sends z to z squared. And there's no fancy, like, I wasn't looking for anything other than, like, hey, what comes out is like there's a function involving something squared, right? It looks like a graph like that. And I run through what's happening there. Um, Basically all it is that the real part is a quadratic function of the imaginary part, and that's it. Um, then the part that I think really tricked people up, a lot of people seem to get this all right. The part that really tripped people up was number 4, which asked the exact same question but with the square root map instead of the squaring map, and said, hey, what do lines parallel to the real axis get mapped to? Well, this is actually it's doable without this trick, but it is harder. It is worth mentioning that you can use problem 3, and was the intention of putting problem 3 right before problem 4. You can use problem 3 to answer problem 4 quite easily. Namely, if you recall, on the first one of the first days, we went through proposition 1.1.3, which told us that every complex number has a square root, or more accurately, in terms of this problem, every complex number is a square. So there's something that squares to it. So if we use the formula we got from squaring up here before, so the real part being, x squared minus c squared, and the imaginary part being 2xc for whatever our constant c is in terms of the imaginary part. all we had to do is say, hey, you can write anything in terms of a square, and then we're just undoing this transformation. That is, if the imaginary part was 2xc, or really 2xy if we weren't setting the imaginary part constant, then all we have to do is say, hey, well, since we can write everything as a square, we can start right there, and then just go, okay, we're writing things as u plus ci for some constant c, and that is we're setting 2xy equal to c, since we can always write things as squares. That is, we can always write things so that they're the square of something. And so then you just solve for y in terms of x, and you're done. It's not bad at all. I think a lot of people got more. Y'all tried to be a lot fancier than you need to be, and I respect that. But yeah. So I'm sorry if that got anyone thrown off. I'm not that sorry, because it seems like it made a lot of you think about math really well, and I'm impressed by that and proud of you. Good job. Um, but yeah. Also, I think that problem 6 threw a number of folks off. It's a L'Hopital's rule problem. You can look through the key if you want. It wasn't it. You don't have to make it as tricky as some of you did. But good job, because I saw people get neat alternative ways of getting to the correct answer, and it was cool. It was cool. Yeah, there's a lot of different ways to do things. So, anyways, that aside, remember that the change to due dates will stick around, and we will continue to do these Sunday due dates instead of um, uh, what we were doing before, where things were all due on Friday night, because we all want to enjoy our Fridays, right? So, anyways, let me make this little window slightly smaller so I don't run out of room quite as easily. Here we go. Let us get into it with section. This is where it starts to be fun. This is why we've been rushing through the first bit with all this background. We're finally going to get into the real meat of an analysis class. That is, we're going to talk about differentiation, which is what, all analysis is fundamentally kind of about, right? The properties of derivatives, and this sort of this process of studying functions and properties of functions by looking at the rate of change of the value of the function. There's like very limits of variation in its input and how that affects the output. So this is a mad important concept. You see it everywhere. It's what enables the 3 courses of calculus that you've taken so far, and will enable the many more courses of analysis you will take if you continue in mathematics. And the nice thing about what happens in C in the complex plane is that, well, I want to be careful. I'm going to say nothing changes, but what I mean is that nothing changes in terms of the things that you are used to working with, and the rules that you're familiar with, and the definitions that you're familiar with. Pretty much nothing is different. The big difference is that when you have a notion of differentiability in the complex plane, this is, unlike in the real case, an extremely limiting thing. In the case of real valued functions on, like function R to R, right? Or Rn to Rn, or Rm to Rn, whatever you want. Differentiability is not that hefty of a requirement. It's totally possible to have a function be differentiable once, but not twice. It doesn't tell you that anything all that fancy. It doesn't even tell you that, like, there are differentiable functions that can't be represented like by a power series. There are, all sorts of different things like this. There's no nice. When you think of a differentiable real valued function, you generally probably only think of something that doesn't have like big jumps or like harsh corners, or some sort of infinite oscillation. It's a very unrestricted class outside of that. The amazing thing is that when we move into complex differentiability, suddenly all of this changes, and complex differentiability, or holomorphy as people tend to call it, is an incredibly limiting condition. It is such a limiting condition that it allows us to study some of the most difficult properties of a large number of objects by merit of the fact that there just aren't all that many holomorphic functions. And when we can associate some sort of quantity or problem that something we're interested in to holomorphic functions, there are so few of them that we're often able to learn things about the thing we're interested in by studying those holomorphic functions. That is, pairing stuff up with holomorphic functions is like a very, very good trick that is very powerful because there aren't enough of them for you to choose the pairing incorrectly, so to speak. Or if you do, it's really like it's a very mild type of incorrectness that you can get, as in contrast to the real valued case. Um, so let's get into it a little bit, and let's start to understand what complex differentiability means. At a surface level, I've had it on the screen for kind of a while here. It's nothing fancy, but we should dig into it a little bit to kind of think about what's going on a little bit more. So if you have a function on a domain, from A to C, where A is an open set. Really, we only need an open set. Let's not even take a domain, which, if you recall, is an open connected set. Let's just take an open set. F is differentiable, complex differentiable, at a point z naught belonging to A, if the limit as z goes to z naught of f of z minus c naught over z minus c naught exists. And this limit is denoted by f prime of z naught, or sometimes by df dz of z naught. So f prime of z naught is a complex number. The function f is analytic on A if f is complex differentiable for each z naught in A. The word holomorphic, we also use that as a synonym to analytic. The phrase analytic at z naught means f is analytic on a neighborhood of z naught. So one thing that your book does this, and I understand why they do. I'll explain it. I personally don't like it, though it is reasonable. They use analytic instead of holomorphic, and I think it kind of steals some of the fun from you guys, because it is a lot nicer just to say differentiable or holomorphic, and then show that analytic, in the traditional real variable sense, meaning has a power series representation, like has a Taylor series, right? That type of analytic. It is much more fun to examine those things as separate and then realize that they are the same. We will get to that. But right now, they end up going, well, we don't want to define analytic and holomorphic separately because, after all, to justify having a Taylor series, you have to have some sort of a notion of differentiability. And I don't know, it's not that unreasonable, but personally, I learned it with holomorphy and analyticity as separate notions that you later discover are the same, and I've always enjoyed that. It's one of the only downsides to this book, and it's just a word difference, so it's not enough reason not to use it. But it and especially since they end up being the same, there's nothing incorrect in the slightest about it. It just it I will probably end up using holomorphic more frequently than using analytic, though we'll use them interchangeably in this class. So that long diversion aside, an important thing to note is that when we're looking at this limit right here, the big piece that we have to care about, and I should be using a color other than white right there, is this z goes to z naught. Think about in R, you've only got, you don't have that many different ways that something can go to a given point. Like if you've got z naught, there might be a lot of different sequences that can, kind of go to z naught, or you can maybe kind of do some fancier way of going to z naught. You could like, I don't know, I'm trying to make sure all these colors are distinct enough. You could like go in and then kind of go way over and then back and then over and back, you know, and slowly get there. Right? There's a few different ways, but like you only kind of have like two directions, you know what I mean? And this is like, remember when we did 1 and 2 sided limits in Calc 1? The the interesting thing about C, in opposition to this, is that C is a kind of 2D world, right? In fact, that's how we started by defining everything. Is we took the complex plane to be R2 equipped with a special multiplication operation, and so now we've suddenly got a whole lot more different like directions to go towards a point. And so this limit is sort of saying somehow that no matter which direction you go, you have to get to the same place. And really it's not like these like little paths, right? It's actually just like sequences of points and stuff. And it's the definition of limits that we were talking about last time for sequences, for functions, whatever, you know, all of the classic pieces we talked about, you know, whether we're talking about the convergence of nets, if you want to be fancy and think of everything like that. We won't need to do that anymore at all. It works out pretty much exactly how you think. Don't worry, I'm glazing over this because it won't end up mattering in terms of anything you do computationally. The important thing to think about though is that what makes this so much more restrictive is that there are more ways you can approach this, and that the ways you approach it are matter more than they do if you're just talking about convergence in, say, like a function like R2 to R2 or something. That is there is a much more subtle difference here, and this is important to notice. Well, here we'll talk about this in just a moment. I don't want to jump too far ahead. I'm getting ahead of myself here. Anyways, the important thing to think about is that this limit as z goes to z naught, this is taken for arbitrary z. It's approaching z naught, but not like along any particular direction. And what we'll see is that the existence of this derivative f prime, you know, the complex derivative of a function implies kind of a lot about a function. For example, first, if it's differentiable one time, it will turn out to be differentiable infinitely many times. That is absolutely not true for real functions and will be a huge difference. But anyways, yeah, so there are a number of theorems that are worth discussing. I will summarize them very quickly. So proposition 1.5.2. Differentiability implies continuity. The way they say it is if f prime of z naught exists, then f is continuous at z naught. This is fair. Nothing too fancy. You expect this from calculus. So proposition 1.5.3. The complex derivative I'll even just say it like this because this is easiest. The complex derivative works the same as the regular old real derivative. And what do they do there? Well, they go, and I'll just bring it over. Let me pull over There we go. All right, so here's this proposition. We'll just discuss it very quick because it's so stinking long. Okay, oops, I've kind of cut off the top, but it says that suppose that f and g are analytic on a subset of C, some open set, right? So they're differentiable. Here's all you need to know. AF plus BG is analytic, so you take sums with A and B, some scalar multiples, right? And it distributes like normal. So the derivative of a sum of scalar multiples is the sum of scalar multiples of the derivatives. If you have two analytic functions, their product is analytic. And the derivative of the product is given by the product rule. If you have a function that is non-zero on a subset, then the taking that function in the denominator with another analytic function on the numerator, you get the quotient. You get that is analytic as well, and you get the quotient rule. If you have a polynomial, well, it's going to be analytic on all of C, and its derivative is given by the usual derivative. So, you know, the classic bring the power down and reduce it by 1. If you have a rational function that is the ratio of two polynomials, it's analytic on the open set consisting of all of z except those points at which the denominator is 0, exactly the same as in the real valued case. And that is what I mean by proposition 1.53 saying that it all works the same. It does. It just works the exact dang same. And you should verify this to yourself. Go look through this section and make sure that you fully feel comfortable with it. There is nothing too bad about any of it. If you feel like you're like, man, do I actually get this? Is this like, am I just like lying to myself or something? Just go through and actually look at the proofs and be like, no, this does what, like, build your confidence that it works the exact same, because I promise you it does. Proposition 1.5.4, this says we still have the chain rule. Okay, so you still got the chain rule. It works the way you think it does, exactly like before. Wonderful, wonderful. And this is why I'm just absolutely booking through these 5 or 6 pages here in your text, maybe a little bit more than that, because all they do is they show that everything you're familiar with continues to hold as it should, and as they should. You know, we should double check these things, but they're easily checkable, and there is nothing particularly worthwhile about checking them in front of you right now during lecture. I don't think any of you will struggle to check them yourselves if you want to on your own time. Instead, what we should focus on to a much greater degree is the interesting consequences of complex differentiability. For example, notice, actually I'll just start with this piece right here, and then we'll do this little notice piece in a moment. Wonderful. All right. So proposition 1.5.5. So suppose that A is a subset of the complex plane that's open and connected. And so that is a domain, or a region as people like to call it, a domain generally. And let F be analytic or holomorphic, if we prefer that term. If f prime of z is 0 on all of A, then f is constant on A. Okay. Let's actually go through and prove this. This is a great little argument. This is actually a very smooth and pretty argument. Let's let z1 and z2 be elements of A. Okay. We want to show that f of z1 is equal to f of z2. Since z1 and z2 are just arbitrary elements, this will imply this will imply that f is constant. That is, if it's equal at any 2 points, then it's got to be constant. It can't change, right? Okay. Let gamma of t be a path joining z1 and z2. By the chain rule, we have that d dt of f of gamma of t, well, this is just going to be f prime of gamma of t, and then pull out the inside, gamma prime of t. All right. Now, this will be 0 for all z and a. Okay. And actually, maybe what we should say here, I think they might even glaze over this. What we should maybe say is that be a path in A. That is, we don't want to jump outside of A quickly. I think everyone probably assumed that, but just to be clear, it has to remain in A. Otherwise, we will run into a problem where we can't say that this piece right here necessarily is 0. All right. So if f equals u plus iv, then well, I should write it like this. Sorry, I'm running out of room here. Basically, all I'm trying to say is that the if the derivative of f of gamma is 0, then the derivative of the component functions of f, so to speak, is also 0, right? So, and this is just a very, I will just write, so by calculus, u and v are constant, right? Or really, I guess I should say by calculus, u composed with gamma and v composed with gamma are constant. Oh, okay. Now, wait a second. If they're constant, then, well, u of gamma of 0 equals v of gamma of 0, and u of gamma of 1 equals v of gamma of 1. So, hey, wouldn't you know it, we've just now shown that f of z1 is equal to f of z2, since gamma is a path joining z1 and z2. Oh, okay. And it's a smooth little argument. So notice, though, there's a very important piece here. We need this connectedness, right? And this path has to lie in A the entire time. And I bring this up because there is, if you don't remember this, then you'll probably use this proposition wrong. Namely, here's an easy one. If we got rid of connected, would we be able to make this wrong? Yes, so easily. How? Well, let's just take A to be, I don't know, 2 different circles, basically, 2 little chunks, right? You just grab 2 chunks in C of stuff. Okay. And then I'll have, on one of the chunks, I'll have, I'll have f of z be equal to 1. And on the other chunk, I'll have f of z be equal to 0. Something like that, right? Then f prime of z is 0 on both sets, on all of A, because it doesn't change on either one of them. But it is not constant on A. It is constant on each connected component of A. So that is what you could really say, is if you wanted to get rid of connected, then you get rid of constant on A, and you get constant on each connected component of A, which is really the same thing. But, I mean, as what we say here, not as getting rid of connected. But yeah, so that's a smooth little trick, and it's important to keep in mind that this connectedness piece is crucial. Um, all right. That doesn't necessarily really bring in the true power, though, or interesting nature of holomorphy analyticity, of complex analyticity. That comes probably, or can begin to be most easily seen through conformal mapping. So this is when you start to see it a little bit, and this is maybe actually the true driver in some ways. The real gist of it, and I will draw a picture here that will probably be kind of horrible. We'll see. The idea is that, let's say we have some point, or actually here, let me put this in a very obvious color. Let's call this a Z naught, maybe, and I'll draw some path going through Z naught, and then I'll draw a different path going through Z naught. So if I've got two curves passing through Z naught, something that I could notice is I could go, oh, okay, well, each of these guys has a tangent, right? There's a tangent. Okay, and then I could get a tangent for the other guy. All right, and then I could kind of zoom in a little bit here. And I could look at this angle. Let's call it theta. So if this is just sitting somewhere in C, and let me draw this a little nicer here. If this is in one copy of C, and I have another copy of C over here, or this could really just be R2, it doesn't matter. There's nothing here that's particularly fancy and importantly complex about it all. Then I take some sort of function f and I map everything over from one chunk to the other. In fact, let's take all of this to be C, just to keep everything consistent with what we're talking about right now. Then there will be some f of z naught. I'm not trying to say that it stays in the exact same place. I'm saying that we're just zooming in on that, where it went. And then these guys might change, these paths. And in fact, I would be surprised if they didn't. But however they do change, here's what doesn't change if we have a conformal mapping. And I hope I can draw this well. I'm going to try. Oh, you can probably hear my son doing a little shriek up there. Poor guy. What's he up to? What's going on? All right. Anyway, so let's see how well I drew this. Probably not as well as I wish I had. Then we get some angle again. We'll call this maybe like theta 1 and like theta 2, right? The idea of a conformal mapping is that theta 1 and theta 2 will be the same. That is, while things can get changed the heck up, the angle between curves passing through points doesn't change. Everything else can get all messed up, but pick any point, look at the angle through the curves, and any curves passing through it, it doesn't change. The picture that everyone likes to show is this picture. It's like you'll find it on like Wikipedia if you look up conformal mapping. And it's probably a lot better of a picture than what I drew. The idea being like, oh, pick like a kind of takes like meshes, sort of, if you want to think of it like that, and it maybe distorts them so they're not like, this nice grid. Just think of how you can like bend a screen, kind of like a window screen, right? Like imagine this is like the screen in your window, and you can sort of deform it like all the heck if you want, but somehow like those little squares, while the wires are getting bent, the property of them being squares like isn't, in some sense. They maybe just are now slightly bent squares, like what you're seeing in here. This is what it means to be a conformal mapping. And I am kind of drawing bad pictures here, but hopefully it makes enough sense. There are a lot of unfortunate pictures that tend to be drawn here whenever everyone wants to start talking about it. Here's the one in your textbook. It's maybe not much better. That it doesn't seem that clear of what's going on. Ultimately, what the idea is the following. If we want to be much more precise beyond these intuitive pictures, assuming they actually are intuitive, here's the definition to be precise. A map F from A to C is called conformal at z0 if there's a angle theta in 0 to 2 pi and an r greater than 0, such that for any curve gamma of t that is differentiable at t equals 0, and for which gamma of t is in A and gamma of 0 is z0, and satisfies gamma prime of 0 is non-zero, then the curve sigma of t given by f of gamma of t is differentiable at t equals 0. And if you set u equal to sigma prime of 0 and v equal to gamma prime of 0, then u and v are the same in modulus up to that factor of r, and the arguments are the same up to that theta there, right? Arg u is arg v plus theta mod 2 pi. A map is conformal when it's conformal at every point. So this is just a fancy version of what I just drew. It looks so much worse when you actually write it. And that is why we probably won't use this except when we particularly need it. However, it does do a lot of it does do a lot for us, and it does a lot to explain to us why, when we show that holomorphic functions are essentially conformal maps, analytic functions, differentiable in the complex sense, these functions are conformal maps. It tells us why the set of conformal maps is so of complex differentiable functions is so rigid, so restrictive, so exclusive, right? Very few complex valued functions are allowed into the VIP club room of holomorphic functions. That's amongst the complex functions, the holomorphic functions are like they're sitting in like the top of the club and ordering expensive bottle service. No one else is allowed up there. It's because of things like this. These are the kinds of consequences you end up getting out where you're like, oh, okay, so I have to preserve every possible angle between any curves that go through these things. Like, this is ridiculous. This is crazy. And this is your book will start to try to redraw similar pictures to what I've been drawing before now. They'll go, okay, well, conformal maps, they preserve angles. They notice here they set it with just one. It ultimately, when they do it with just one, it's just picking a different path. But what they're, so it's the same thing. It just says, hey, the angles get changed up, get rotated perhaps a bit, but, things get rotated, things get stretched. But infinitesimally, no matter how you approach a point, if you approach from two different directions, the angles between those two different directions gets preserved under your mapping. And so this is obviously a ridiculously restrictive condition. And as we will show, the poor little guy's going wild. You all right? Okay. Aw. Son's having a fit. My poor long-suffering wife is a saint. All right. Here, 1 second. Let me get this ready for us. All right. All right. And as I've been saying, and this is the content of the conformal mapping theorem, a function f from a to c that's analytic, and this is the part I've kind of been glossing over, has a non-zero derivative at a point z naught, is conformal at z naught, with this angle theta in the definition of conformal given by the argument of f prime of z naught, and the radius given by the modulus of the derivative. Okay. If you want to break down what this means, it looks really messy to do so. But sorry, just getting distracted by something here. So the confusing part of doing video lectures is if we were in person, everyone would hear the same things and stuff. Anyways, yeah. The idea here is just essentially to build some intuition for what the derivative is telling us. The same way that we built intuition for like what multiplication of complex numbers does geometrically. This tells us, geometrically speaking, what the complex derivative is telling us. That is, if the theta is the argument of the derivative at a point, and the r is the modulus, this is kind of like saying, hey, well, the rate of change, it's in terms of what it's doing to the arguments, the angle of approach, right, of a curve, it's just moving it by theta, and then it's stretching everything by its modulus, right? So in another way, and this is probably the much easier way to say it, let's recall, sorry, I got thrown off for a second there. What the Jacobian of a function is, df. Some people also like to write it j sub f, whatever you like. I like j sub f, but your book writes df, and most people also seem to. This is the matrix of partial derivatives of your function. Partial, that's a v, just to be clear. That's not a u. Partial y. Oh, my pen apparently is jinking out on me right there. All right. Oh, okay. There we go. Yeah, so recall that the Jacobian, or matrix of partial derivatives of a function, here where we have f of, we'll write it as f of z, is equal to u of z plus I v of z, right? This usual way of writing it, the real and the complex part of your function. This matrix of partial derivatives, treating each of these u's and v's as functions of x and y, where z is x plus iy. They're functions of two real variables, and they spit out one real value. From the point of view of real variables, a function f is differentiable if you can build this matrix and it's the best linear approximation. You can do this in the standard epsilon delta, if you recall all that stuff. You don't have to think about that too much right now. The idea here, though, is that we can connect what we just learned about conformal mappings to the Jacobian matrix and derive some very important equations that will be absolutely crucial to the rest of the class. These equations are called the Cauchy-Riemann equations, and they are a really big deal. Essentially, they give us what's going on then with this conformal requirement. They end up implying it, and you can actually do it the other way too. And they let us know that basically what happens is that near a given point, infinitesimally, the complex differentiable functions are a stretch and a rotation, and that this is the restrictive piece. So they can vary. They're not just they're not globally stretches and rotations, but infinitesimally at a point they are like a stretch and a rotation. That is, if we go back to our picture of conformality, they are. Oh, have I made a mistake? Okay. They might stretch things out. They might rotate things a little bit, but they keep angles the same. They just kind of wiggle around a little bit near points. Just turn it, just stretch it a little bit. That's all. It's like the weird picture of the window screen, you know. Anyways, if we want to move on very slightly, and I think we're probably actually at about, we're at like the end of class. Here, I'll throw up the Cauchy-Riemann theorem, and we'll talk about it next time a little bit more. Here's the big takeaway of this chunk, and this is what we really want to get into. So suppose that A is an open set in C and f is a function from A to C. Then f prime of z naught exists if and only if f is differentiable in the sense of real variables at x naught, y naught, a z naught, and the functions u and v involved in f satisfy partial u partial x is equal to partial v partial y, and partial u partial y is equal to negative partial v partial x. So thinking about the Jacobian, does anyone recall something that involves multiplying, say, like partial u partial x partial v partial y, right? Is there some trick? Like if you take a determinant, right? Maybe if I take people often represent determinants with bars or write det. Notice that this will do partial u partial x partial v partial y, and then you'd add on partial u partial y partial v partial x. But hey, wait a second. These Cauchy-Riemann equations right here, they're going to tell us something very interesting. Namely, partial u partial x and partial v partial y are the same. So this right here is really, and this is where it gets kind of cool, you could just cross out this piece and square this. And over here, partial u partial y is negative partial v partial x. So this is really just maybe like minus this piece squared. Oh, or if you want to do that a different way, you could just, do it like this. Hey, wait a second, I've done everything in terms of u's. Oh, whoa. But look, I could just as easily do the same the other way and do everything strictly in terms of v's. Basically, it says that these two things, the u piece and the v piece, the real and the imaginary part, have to satisfy, and I should have crossed this out and made that a minus too, have to satisfy some very nice conditions with respect to each other. They have to essentially, the Jacobian has to work out to a difference of squares in a certain way, in this way in particular. And this is a very restrictive condition that will give us a lot of interesting things. We will talk about some of those things next time, but in a very general sense, that is the rest of the class. The rest of the class will be exploring consequences of this uh, this set of equations in a big way. This is really the powerhouse of complex analysis, and maybe some people will, not want to talk to me for saying it like that because it makes it sound so much less grand and cool than it all is. But this is the powerhouse of complex analysis. These equations, you should know them so well that you don't have to worry if about like deriving them, or like have to think about whether or not they're true. It should just be so automatic and obvious that if you're dealing with a complex or a holomorphic function, that well, of course you have this. It should be so complex and so automatic that it becomes difficult to not assume this. Um, get used to these guys; they will appear a lot, and we will beginning next week, or not next week, next class, talk a lot more about them. So there we go. I guess we'll call it quits for today. In terms of the lecture, I'll stick around here for a moment in case anyone has any questions to throw in the chat. People have been scheduling office hours with me, which I appreciate. Please take advantage of that. If you, I notice a few people are maybe falling behind a little bit. If you are, don't worry. It's not too late. Hit me up. We can work on it. And yeah. I'll wait around for any questions. If you have any, otherwise, just shoot me an email. Okay, I'm not seeing anything in the chat. Um, so I guess we'll call it for the night. Keep it real and have a good one.